Hello everyone and welcome to the first video for AP Calculus. This video goes with section 1.1 of the textbook, the Larson textbook, and it is a preview of calculus. So this is really going to be looking at the big picture of what calculus is. So our objectives for this particular video: 1, understand what calculus is and how it compares with pre-calculus. Number 2, understand that the tangent line problem is basic to calculus. And number 3, understand that the area problem is basic to calculus as well. Now let's take a look at comparing pre-calculus and calculus. First of all, when we look at one of the things that we have in pre-calculus, what we looked at is the motion where you had a constant velocity. Last year I mentioned to you, if I said that you started right now, you drove 1 hour and you went 60 miles, I asked you in terms of what was the speed, you told me 60 miles per hour, which was what we have in terms of a pre-calculus problem. A calculus problem is where we're looking at the motion with a variable velocity. The idea that a car starting from Fenton High School and going 60 miles away is traveling at the exact same speed that entire time is not possible. So that's where calculus comes in. We're looking at what happens when we have a variable velocity. In pre-calculus and even before, you dealt with the slope of a line. In calculus, we start talking about slopes in terms of how they relate to a curve. So we find the slope of a curve. In pre-calculus, we could look at the curvature of a circle. And in calculus, we looked at the curvature of a general curve. In pre-calculus, we found areas using rectangles or other geometric shapes. And in calculus, we'll find areas under the curve. And what you're going to see, if you look in your book on pages 43 and 44 of your textbook, you'll see other examples of things that we can, what we did in terms of pre-calculus problem versus its calculus equivalent. The big thing that you need to remember is that in terms of this, we have this in mathematics, we have our pre-calculus mathematics, the stuff that we worked on last year and the things you've actually done really up until all the way through last year. We add in one thing, and that one thing is the thing we started talking about at the end of last year. It's called the limit process. We add in that limit process, and that's when we get this wonderful world of calculus. What is calculus? Calculus is not just memorizing a set of derivative and integration formulas. Those are the two main concepts in calculus that we're going to deal with, derivatives and integration. It's not just memorizing the formulas, although that will come into play, and that is a part of what we will do. You have formulas you're going to have to memorize, but it's not just that. Your goal in this case is going to be to learn how the pre-calculus formulas and techniques are used as building blocks for calculus formulas and techniques. In other words, your goal is going to be, as we go through and look at a particular topic, is going to be looking at that and saying, okay, this is what I did in pre-calculus or before, and this is how I'm going to modify that with that limit process to develop this calculus concept. By doing that, it will help you with your understanding of calculus. It'll help your self-confidence going forward, and it will actually make it much more fun. Now we're going to take a look at the tangent line problem. This is the first of the two problems that we're going to look at. In the tangent line problem, the idea is that we want to find the slope of the tangent line to a curve. Now that slope of that tangent line is also called the instantaneous rate of change. Now the problem that we know in order to find slope, we need to have 2 points. And we know we also cannot divide by 0, so we can't use the same point, if you will. So what's going to happen here to identify that tangent line? We're going to use secant lines. Secant lines are lines that connect 2 points on a curve. So I've labeled on this curve here, which is what we're going to be working on. We want to find the slope of this curve at this particular value here. And I've labeled 2 points on the curve. One was x f of x, and the other is x plus delta x, f of x plus delta x. And what's going to happen on this one is that we're going to go through and move this point. We're going to move that point closer to our other point, and that is what will allow us to find that help us approximate the slope of the curve at this particular point. Well, to do that, we need our slope. So the slope formula in this case, our slope of that line, slope of line L, is just going to be the change in y over the change in x. So it's going to be f of x plus delta x minus f of x all over x plus delta x minus x. And when I simplify that, I will get f of x plus delta x minus f of x all over delta x. And that right there should look familiar to you, because last year at the end of the year, we were looking at this particular thing. It was called the difference quotient. And that's what we're going to use to go through and help us solve our tangent line problem. Let's look at an example of, in terms of a tangent line problem, helping us identify, coming up with an idea what the slope of the tangent line at a particular point on a curve is. Now in this example here, we're just going to use f of x equals x squared. And you can see I've graphed it here. I've labeled some points. The first point, the point we're going to be looking at, where we want to find the slope, we want to approximate the slope of f of x equals x squared at the point 1, 1. I've labeled some points. This is the point 2,4. There's 0.39. I also have a general point here. That's the point that we're going to be using. That's the x plus delta x, f of x plus delta x. Only this time it's going to be x and x squared. And what's going to happen here is we're going to be taking this and we're going to connect this point and that point with a line. So let me give that a try here. So it's going to come up like this. Go through there. Pretend that's a straight line. We're going to connect that with a line, and that line is going to have a slope. And the slope of that line that connects that 1, 1 with the point x squared is right down here. It's that. So now we're going to use that to go through and estimate slopes. So if I said by using different values of x, so in this case, if I let x equal 2, then I can plug 2 in for the x's there. So I'm going to get my slope m equal to 2 squared minus 1 over 2 minus 1, which will equal 2 squared is 4. So that's going to be 4 minus 1 over 1, which comes out to be 3. So I know the line that would connect 1, 1 with the point 2, 4 is going to have a slope of 3. I also want to do that now for these other ones. Let's look at 1.5. If I use 1.5, my slope m is going to be equal to 1.5 squared minus 1 over 1.5 minus 1. You can take that and you can put that into your calculator. So pause the video and do that calculation for me. When you did that, you should have come up with 2.5 as a slope. So if I connected the point 1, 1 with the point here at 1.5, and then it would be 2.25 would be the y-coordinate, I would get a slope of 2.5. What I'd like you to do now is pause the video, and I want you to find the slope of the line using these three values for x here, 1.1, 1.01, 1.001. So pause the video, calculate those slopes. Welcome back. As you did that, what you should have come up with for when x equals 1.1, you should have gotten a slope m equal 2.1. When x was equal to 1.01, that slope should have been 2.01. And when x was equal to 1.001, that slope should have been 2.001. 0.01. Now you might notice a pattern already happening here in terms of the x values here and what the slopes came up to be. And that can be, you can confirm that pattern just by taking a look back here at this particular rational slope function. We have x squared minus 1 over x minus 1. Well, you should recognize that the top is a difference of two squares and that you can factor that and reduce it, and that in effect, that in reality, that is equal to x plus 1. And so that way you can see why it has been going up by 1. But that's the idea behind the tangent line problem. We go through, we used a pre-calculus topic, the slope formula. We apply the limit process, which is what we're doing here by moving things closer and closer to 1, and we can approximate the slope that way. And by looking at these values, we can sit there and get an estimate of what that slope would actually be. The next problem that we have is what's called the area problem. We're looking at the area between a curve here, y equals f of x, and the x-axis. Now when we take a look at that area, in this case I'm looking at the area between the curve and the yellow lines. When I look at that, the way we can approximate that area, and that's really what we're going to be doing at this point in time, is we can approximate it using rectangles. Now we can choose rectangles how we break up the region that we're looking at is up to us. We can break it up in any way we want. Often you can use what's called a regular partition where you break it up into equal pieces. Obviously, I did not do that with this one. So we can also, would be an irregular partition or a general partition. And what we do is we can go through and we just have to calculate we have to identify a rectangle that we can use to approximate the area within each subinterval. So I want a rectangle here that can approximate that area. Well, one of the things I can do in this case is I could go through and I can really make the rectangle wherever I want. I can go and say I'm going to use this for my top. So this is the rectangle I'm going to end up using to calculate that. So I can calculate, I just have to know what the height of the rectangle is. I'm able to identify what that change in x is. This would be delta x1. And so the area there is going to be delta x1 times whatever we get for the function value at this particular point where we're calculating our height. We can go through and we can always stay below, or we can go in the middle if we choose. We can go and say, I'm going to use this rectangle that goes here. So I'm just kind of using the other side as a height. So I'm using the top point here where this red line touches the curve to be the value that's going to give me the height. I go across and I get another area. So I have that rectangle right there. I can go between the two. I could go right here and look at that in terms of the area and calculate that one. Or I can just go and use another endpoint or use the highest point in there. And that would then give me another area. And to go through, and then what we do with the area problem is we calculate these areas of those rectangles and we add them up. And that will give me an estimate of what's happening. What we can do to go through and make this a more accurate estimate, the more rectangles we use, the more accuracy we're going to get. So if I go through and say, okay, I've broken this up into 4 rectangles, I can get a good representation. I can get a good approximation of the area. If I use 10 rectangles, I'm going to get a better approximation. If I use 100 rectangles, I get an even better approximation. Okay, and that's the idea that happens with the limit process. Let's look at an example of this, and we're going to really look at in terms of 2 examples that we have, 2 very common ones that you deal with. The function we're going to be working with in this case is f of x equals x squared, and I've identified we're going to have a regular partition. We're going to find the area between f of x equals x squared, we're going to approximate the area between fx equals x squared and the x-axis from 0 to 4. So we're going to use a regular partition, which means that we're just going to change x. The base of my rectangles I'm going to be using is going to remain constant. In this case, that base is going to be 1. And now I've drawn 2 sets of rectangles here. One set is what's called an upper sum because it's going to be bigger than the true value of the area between the curve between x squared and the x-axis. And that upper sum is what you see would be the rectangles in green. And so the area of the first rectangle, so I have my first rectangle is here. I have a second rectangle here, third here, and a fourth one there. So the area of the first rectangle is going to be my base is 1 times my height. Well, yes, the scaling isn't the same. My height is also 1. So the area of that first rectangle is 1. Area of the second rectangle, the base is 1. My height in this case is 4. So 1 times 4 is 4. Area 3. Base is 1 because it's a regular partition. The height is 9. And area 4 is, my base is 1 and my height is 16. So it's 16. So if I add up 1 plus 4 plus 9 plus 16, I get 30. So my one approximation that I have for the area between the curve between x squared and the x-axis from 0 to 4 is 30 square units. We recognize that that is an overestimate. Okay, we can also go through and do another sum. The other one is called the lower sum, and that's what you see with the orange on those. Now the first thing you're going to want to notice here is that you might notice there's an orange line right there, right on the x-axis. And that's the case because we're going to be using the right-hand endpoint on this is going to give me that lower sum. So in this case, when I'm working on this, my first rectangle, when I do that, the right hand or the lower, in this case the lower sum, area 1, my base is 1, but my height now is 0. So I'm going to get 0. Area 2, my base is 1, and the height is 1, so it's 1. Area 3 is going to be 1 times the height is 4. And the fourth rectangle that I have, this one right here, that is going to be the base is 1 times 9 equals 9. And so when I add those up, I get 14. So another approximation we would have for the area between the x-axis and the curve, y equals x squared, would be 14 square units. Now keep in mind again, in this case, what you saw in green, which we called the upper sum, was also a left-hand sum because we only just used the left-hand endpoints of each subinterval. The one in orange was a right-hand sum and is also the lower sum. We know when you use 4 rectangles, I am not going to get a sum that's lower than 14 or bigger than 30. In other words, I know that the true area is somewhere between 14 and 30. Different ways of going through and choosing your endpoints can give you a different approximation. Obviously, you could be sitting there saying, well, why don't we choose something other than an endpoint? That would give us a better approximation, and that's true. In this situation, we could. But for right now, we're just going to be content with saying that, oh, our true area is between 14 and 30. So with that, this does conclude the first set of notes for AP Calculus this year. Make sure that you are comfortable with the calculations that I've done and the processes that we've illustrated here. If not, make sure to note those with a red star or some sort of mark in your notes so you can be sure to ask about them. And with that, I will see you in our next class.